Jnanam paramam dheyam. Knowledge is supreme.
So today I am just going to continue. I gave you a brief flavor of how to construct tensors. Familiar ones are your scalars and vectors to you, but you can also start constructing higher indexed object by taking products of these vectors is what I kind of gave you a flavor, right? So today what I am going to do is I am going to try and formalize and tell you about tensor operators. Okay. Even though it looks abstract, if you remember scalar and vector and how I constructed moment of inertia tensor for you, you will know how the higher tensors can be constructed. Is that clear? Quadrupole moment is called quadrupole moment tensor, right? You have done the multipole expansion. Dipole moment is a vector, then quadrupole moment, then you have these higher moments. Those are all tensors. Okay. Just to give you some more examples. So what I want to do is, we have talked about selection rules, which transition is possible under parity and so on. So this is formally for rotationally invariant systems. You can put it in a form of a theorem which is called Wigner-Eckart theorem. Okay. So these two are the themes for today's lecture, and let's see how much I can progress. Okay. Okay, just to recap what we did for the states. In the context of states, if you take two spin half particles, you can either look at it as an uncoupled basis. This is J1, J2, M1, M2, the notation. Now I am going to blindly follow this notation. And there is a coupled state which is equivalent to again J1, J2, but you can call it as J or S because I am looking at spins. I put it as S equal to 1, M equal to 1, and this is what is the stretch state. And then on the stretch state, we operated ladder operators. On the left hand side is a coupled state, right hand side is an uncoupled state, and then we did this S minus operator on the coupled state. It only looks at these two. And the right hand side, S1 minus will operate on the M1 and reduce it to M1 minus 1, and S2 minus will operate on M2 and reduce it to M2 minus 1, right? So we can do this, and we did this elaborately, and we found that the coupled state, this is a stretch state, and then we get the coupled state with one lower of this magnetic quantum number, which is 1, 0, in terms of the uncoupled basis states, and these coefficients are what we call it as a Clebsch-Gordon coefficients, and we could write the Clebsch-Gordon matrix. I would like you to do the spin 1 and spin half, the Clebsch-Gordon coefficients. Okay, take one of the particle to be spin 1, another particle to be spin half, j equal to 1 and j equal to half. Compose, write the stretch state, do the ladder operation, find all the CG coefficient and write the matrix completely. Yeah, and then we also went on to say that how do we find there is also one more state which we have to worry, this 1 minus 1. Again you can get by the ladder operation, lowering operation. You can get this and you can show that it is exactly equal to this with coefficient 1. And to determine the coupled state with total angular momentum 0 and magnetic quantum number 0, how do we do that? This state has to be orthogonal to this state, and using that you can fix that there is this coefficient with a relative sign, and that is what we did. So these three states correspond to spin j in the coupled state, and then m equal to 0 is the only state, and that state is a linear combination of these two with the negatives. So redoing this is a very simplest example, but I want you to do it for taking this to be 1 and this to be half. I want you to do that. Okay. So now we will take a look at tensor operators, where there is a lot of correspondence between the states and the tensor operators. Okay, so this is something which we already discussed in the last lecture. How do we define a scalars in classical mechanics gets promoted to what is scalar operators in quantum mechanics, that operators under any transformation will have the similarity transformation, and you know the operator which does the rotation, which is a unitary operator which is dependent on the theta angle. And in doing this transformation, if it is a scalar operator, it should remain the same. A prime should be same as A, which means if you expand the this u of theta as e to the power of I j dot theta, you can show that scalar operators will commute with all the components of angular momentum. And you have verified this for r dot r or a dot b, and it is nice to know that this is the formal way in which you can give a proof that scalar operators will commute with angular momentum. Any questions on this? Step I probably indicated in the last lecture, but you can do it. So now what happens to the vector operators? Vectors in classical mechanics transforms like the components of a position vector, any vector, and the corresponding vector operator should transform like the position operator. So if you try to put that in, then you have how the A prime will transform, you know how the A prime or a position vector transform, this we have elaborated. So from there you can deduce how the commutator of the generator of rotation, which is angular momentum, and the position components, how do they behave. Whatever is this behavior, it's the same behavior for any vector including angular momentum. Right? Angular momentum is also a vector. But angular momentum is an axial vector, that to see that you have to do a parity transformation. Under proper rotation, there is no distinction between a polar vector and an axial vector. Only when you do parity, things will start showing differences. Right? Is that clear to you, all of you? In classical mechanics, I am sure you would have done this, no? So if you have A cross B under rotation, call this to be a new vector. Under rotation, Ci will be Rij Ck, where Rij are the rotation matrix in classical mechanics. Right? So this is also a vector under proper rotations. The only difference between A, B and C is that A and B are polar vectors. Under parity, if you call parity, on A will give you minus C, but parity on C will be C itself. It doesn't change sign. So this is why this is called polar, this is called axial. And all C as well as A or B, how it transforms under rotation is exactly the way the position components transform. There is no difference. Okay. So that will tell you how to find the commutator of Ji with Aj. So this will be IH cross epsilon Ijk, and it will be the Ak. Okay. This I wanted you to check. I did not do this for you, but I gave you an indication that you know how to do it for R, and instead of R you replace it by A and you can do this. So what is this commutator? And the same holds for any vector operators. So for example, position vector, linear momentum, angular momentum, vector potentials are all examples of vectors. They are also vector operators in quantum mechanics. Scalar operator you can construct out of vectors by taking a dot product. Right? if you take a dot product of two vectors, you get a scalar which does not change under rotation. So this is also something which I want you to. So you have to show that Ji with A dot B. Prove this. With Ai you know what is the transformation with the components of the A vector. With the components of the B vector you know what is the transformation. And you know A dot B behaves like a scalar. So you should be able to show this, that Ji with A dot B is, what is it? 0 or non-zero? 0, right? It has to be 0. So please prove this also using this. This way you will get a handle on how to play with commutator bracket, and you know the answer, you are verifying the answer. R dot P is a scalar, so R dot P has to commute with J. You can also do R dot B with R cross P also, but instead I am just asking you to do how any vector operator transforms with respect to the angular momentum. You know that algebra, so why don't you use that and see why A dot B commutes with Ji. It's not obvious, right? But there will be product of two epsilons, and you can use the, you have done the algebra of epsilons, right? Levi-Civita products, use those and you will be able to show this. Do a little bit of algebra and you will be able to show it to be 0. So scalar products, examples, radial component which is square root of R dot R, R dot T, A dot P, A dot B, all kinds of dot products. They are all scalar. Okay, so now I am slowly getting on to you on a notation, and then I will give you some examples, that way you will understand what is going on. We are going to call a tensor operator to be a tensor operator of rank k. Okay, so take this as a definition. So we write T in bracket, we have two integers or half odd integers because operators are always going to be integers. So k is always a positive integer that gives you the rank, and q, just like your angular momentum, runs from minus j to plus j. Q is restricted to take values from minus k to plus k. All operators with integer k, which I will call them as a tensor operator of rank k, and the q will take possibilities from k to minus k in steps of 1. For example, the familiar scalar operator can be called as a tensor of rank 0. Once it is rank 0, the q will also be trivially 0, so it is one component. It is just one. If I take a vector operator will be called as a rank 1 operator, and q will take values minus 1, plus 1 and 0. Is that right? According to that definition which I have given in the first bullet. Now you will ask, suppose you take the position vector, you know that the components are x, y and z, but to make contact with this formal notation, it's better to write as complex coordinates. We'll see why we are doing this. Z component is t1, 0, the z component is t1, 0. The t1 with q plus or minus 1, we will take it to be this, and we'll see why this is true. Okay. We'll also see why we are doing this. I want you to do this for the position vector. At least check for the position vector where t1, plus or minus 1 is this, t1, 0 is z. Please check what we get. So let's do it right away. You can write a vector as ax, ay, az. Okay. You can also rewrite this as, you can write this as a tensor of rank 1, q with az, which is which belongs to T of 1 comma 0, and let's write this as plus or minus AX minus IY IAY. So this is plus and the other one is minus, so that becomes, okay. So let me write T1 comma 1 for this vector A is minus AX minus IAY. T1 comma minus 1 is AX minus IAY, and T1 comma 0 is AZ for any vector including position vectors. If you want to write it for position vectors, this will be X minus IY, X plus IY and Z. This is just a convention. We will see why this convention is. See. Then I would like to look at JZ with T of something wrong. Did I make a mistake? Yeah, this is minus IY. Thank you. So now do JZ with 1 comma 1. What are you getting? So take it to be minus X minus IY and JZ and do the commutator. So T11 with H cross. What about JZ with T10? That is 0 times 0. Is that right? The JZ with this is 0. What about the last one? Minus H cross 1 minus 1. Correct? Is that right? So can we write this compactly? We have 3 data here. So can I write this as, tell me how do I write this compactly? JZ T1 comma Q will be QH cross T1 comma Q. Anything wrong? I can do this. Now my claim is that this will hold even if I do for other tensors of rank K, QH cross T K comma Q. I am not proven, but it can be proved. Is that all? You need to do other things also. What are the things? J plus or minus with T1 comma Q. What will this be? Is the next question. Why am I doing this, The reason is that we will see your J plus on your JM state. This was giving you some coefficient on J M minus 1. M plus 1. I want to see whether the tensor operators also has a similar property. Since you know the position components, can you please verify what you get here? And can you check whether we can write this as, informally if it is K, I would have put K is 1. So let me write this as 1 into 1 plus, no, this is J plus K plus Q or K minus Q? K minus Q? Minus plus. Anyway, I am very bad at all these signs, but you can help me out. Which is plus and minus? This is correct? On H cross T of, if this is K, then my claim is it will be plus or minus 1, Q plus or minus. So this is my guess. The guess is done. from thinking that there is a one-to-one correspondence between states and operators. If that is the case, then my operators, commutator algebra with the components of your angular momentum, they have to have these properties. Incidentally, you should go and check what is these things. Formally, you know the differential operator for L plus, right? You can write a differential operator for L plus, and you know what is YLM of theta phi. Take L equal to 1, do the L plus and check what you get, what is expected. You can write the YLM theta phi as some unit vector whose direction is given an LM, and you can operate L plus. This unit vector gives you the direction which will give you the theta and phi. In the angular momentum algebra, L plus on LM you all know, but I am asking you to write the differential operator position basis and operate it on YLM of theta phi, which you have done in your first year course or as a wave function formalism. So both the ways should match, right? So you can check that this one will give you a YLM m plus 1 theta phi. But what the coefficient I am not writing, but you can check it out. It will be exactly same as this. There is no change, but you can verify it. For at least for L equal to 1 and L equal to 2, you can play your hands on seeing that the spherical harmonics are also called spherical tensors. I am sure you all have heard that they are spherical tensors, right? So you can take these spherical tensors here and look at the commutators. So these are ways of trying to show that there are a lot of resemblance to the angular momentum states, to your spherical harmonics, and spherical harmonics were coming out naturally in writing your orthogonal basis functions, right? Did not look at writing all possible polynomials, but some linear combination which gave you the nice, and this is what comes in your multipole expansions also. Is that correct? Dipole moment will involve spherical harmonics of L equal to 1. Then the quadrupole moment will involve spherical harmonics of L equal to 2. When you do the multipole expansion, I am just trying to connect various ways in which you have seen this. There is an expansion which has this neat way of breaking into L equal to 0, which is a scalar, L equal to 1, which is a vector, L equal to 2, which is a spherical tensor of rank 2, and so on. Okay? Okay, so this I am leaving it to you as a practice thing to check how the tensors formally do it for k equal to 1 and then generalize it. I am not asking you to prove in general for any k, but it can also be done. But right now you do it for k equal to 1. This we have already verified. This I want you to do. I have given you the answer. Please verify that that happens for k equal to 1.